are posted. I'm going to choose the most complicated one, which is this polynomial that is minus x to the fourth, minus x to the third, minus 24x to the second, and then minus 16x. So I'm going to go over to Desmos, first of all, and type that in. So you have to have, right, so once you have your polynomial typed in, it appears, and so I'm going to see if this makes sense to me. All right, so I see a 0 at minus 4 comma 0, and it bounces, so I know that's really two zeros. And then I see a turning point, and then I see a 0 at minus 1, 0, and it crosses, so that's a third 0. And I see a turning point, and then I see another 0 at 0, 0. So that's my fourth 0, which is good because this is a fourth degree polynomial, because that's my highest power. And so I expect there to be four zeros. So we have 3 0 locations and a total of 4 zeros. So one of our zeros is going to have a multiplicity of 2. All right. So I have got 0, a 0, and a 0. And I have a turning point. And if you don't click on anything to begin with, Desmos really knows which are the important points. And so you can go in and just click on the gray points to see the 2 turning points. They'll all disappear in a minute. I should in the different order. But anyway, so then I want to have an input table. So I'm going to do the plus sign and a table. So this table, x1 is going to be my input value. And for every input, I want it to evaluate using my rule, f of x. And so this tells Desmos whatever number I type in here, if I put in a minus 5, it says, well, put minus 5 in for x and figure out what f of x is at that point. So the output, if I put in minus 5, is going to be minus 20, which now appears as a dot down here. All right, so when you make a table, you actually have a lot of freedom. You can put in lots of different choices of numbers. I'm going to go ahead and put in minus 2. I know I have a 0 at minus 1, so I'll put that in for sure. I always put in x equals 0 because that's your y-intercept. In this case, the point 0 comma 0 is both an x and a y-intercept. And then I'll do 1, and then I guess I'll put in 5. All right, so now we have a nice table. Got my equation up there. And I'm going to go back and click on the values that are important to me so that they're, when I grab the screen grab, they'll all be clicked on. All right, those are my 3 zeros. So up here, I have, that's one of the turning points. And there's my other turning point. All right, so now that I have it graphed, I'm going to cut and paste, and I'm going to actually do this as 2 separate cut and pastes, just to make it kind of nice in the image. And I know my graph space is fairly square, and so I'm going to grab this for the graph. Hit Control C. Go over here to Desmos. Put it up towards the top, and then I need to make it a little bit smaller so it fits. And I'll center it. That looks good. And then I'll go back to Desmos and grab my table. And there's the table. And Control C, Control V over here. Move this up to here. And make that so it fits in the square. And then line it up in the middle. All right, so now my top is finished. So to fill in the bottom 2 quadrants, and so the top left right here is numerical solutions, and so every single one of these ordered pair points, so the point at minus 5 comma minus 20 on the graph is a solution to this polynomial. If I put in x equals minus 4, then I get 0 as the output, and so that is also a point that's graphed here. If I put in x equals minus 2, I'm going to get minus 8, and so on. All right, so for factored form, that means I am going to write out all my linear factors, and they're defined by the zeros. I have 3 zeros because I have 3 places where it crosses or bounces at the x-axis. I can see in the graph. So I have a 0 at 0, 0, and I have a 0 at 1, minus 1, 0, and then I have a 0 at minus 4, 0. All right, so at 0, at x equals 0, it crosses. At x equals minus 1, it crosses. And at x equals minus 4, it bounces. And so, like I said a little while ago, that means I have a double or a multiplicity of 2, 0 at 4. All right, so the way we usually write this is we're going to write our x term first. And so the linear factor, if the 0 is at x equals 0, is just x. The linear factor at x equals minus 1 is x plus 1. And the linear factor at minus 4 is x plus 4. Remember, the linear factors are the places where it has an x-intercept, and because these are all multiplied together, they're called zeros because if any one of these parentheses turns into 0, that makes the function, forces the function to be 0. And since we know that happens at x equals minus 4, we know there has to be a linear factor of x plus 4. And since we know one happens at x plus 1, we know that it happens at the value x equals minus 1. The only way that can happen is if the linear factor is x plus 1. And since we know we have a 0 or an x-intercept at x equals 0, the only way that happens is if the linear factor is just x. The one at x plus 4, or the one that's located at x equals minus 4, because it bounces, we know it has to be an even multiplicity, so 2, 4, 6. It could actually be higher than 2. The reason I know to stop at 2 is when I look at this polynomial, it's a 4th degree, and so I have to have a total of 4, including multiplicity roots or zeros. And so I have 1 at x, I have 1 at x plus 1, and that leaves 2 at x plus 4. All right, so degree we've already mentioned a couple times. That is, if you're looking at standard form, it's the exponent highest power, and leading coefficient is the number that multiplies the x term with the highest power. So in this case, our leading coefficient is minus 1. Our zeros and roots, there are 3 of them. And we have 1 at 0, 0. And then we have 1 at minus 1, 0. And we have 2 at minus 4, 0. Domain is all real numbers, and that's actually true for all polynomials. Range is what are the possible output values. So since this is an even function, and we can actually see it here, there's a bound. So range is what are my possible output values, and so it's bounded here. Like I only get output values below that boundary. And so my range is going to be, it goes all the way down to minus infinity, so we can start there. So we have minus infinity and y, so y is greater than minus infinity and also less than the turning point, which is the y value is at 3.124. Right, so that's our range. End behavior. Well, as we look as far to we put in bigger and bigger x values, what's happening to the function is it's going down. And so it goes to minus infinity. And the same is true on the other side. As we look with bigger and bigger negative numbers, the function's also going down. And so as x approaches minus infinity, f of x also approaches minus infinity. So that's our two end behaviors. And then a y-intercept. That is the place that crosses the y-axis, or it's always the place where x equals 0. In this case, 0, 0. Right, and our last thing is our turning points. And so we have a turning point at, I clicked on them. So the first one's at minus 2.3, and I'm going to round minus 8.6. That's the first one. And the second one is at minus 0.43, comma 3.1. And maybe a little bigger so it fits. All right, so the turning point was important actually when we figured out range also. This actually is 3.1. And so just to make it match, since I said my y value here is 3.1, so that's my bound up here, I'm going to go back down here and round it to 3.1 so that they match. That's for anybody who doesn't look at the video. All right, intervals of increasing, always x values. So if we always start way over on the left, and way over on the left at very, very negative x values, we're going to start increasing. So for x starting at minus infinity, the function is going to increase all the way up until we get to, it's actually a turning point here, which happens at minus 4. So one of the zeros, because it touches and bounces, is actually a turning point. And from that point, it decreases. So from x equals minus 4 all the way up till the x of minus 2.3, it decreases. And then we're increasing again. So you'll notice that the intervals always start next to each other. So at x equals minus 2.3, it's going to turn. And then it's going to increase until we get to the last turning point, which happens at x equals 0.43. So that interval stops at x equals 4.3. And then we have a final decreasing interval that starts at 4.3, and it continues until x goes to infinity. And those are our intervals. All right, hopefully that wasn't too long. Thank you for coming.